Welcome to Industrial PLC Applications. This video is on addresses, aliases, and variables and data types. This is part 2. With variables that are not system variables or addresses, there are a number of factors that you must keep in mind. How much memory does the variable represent? What kind of information does the variable store? Simple data or complex data? How do you want the data to be displayed? Is the variable a construct? When you create a new variable, you define the variable's numeric range, the amount of memory the PLC must commit, monitor, and manipulate, and its constituents. It determines the largest amount of data that can be assigned to a block of contiguous memory bits. An assembly of contiguous data is called a data type. Simple variables represent simple values. The amount of memory involved depends on the number of contiguous bits that are used. Here's a new term that we should get clear: digital. Digital is a system of signals that involves a single change of state, 0 to 1 or 1 to 0, as in no voltage to full voltage or full voltage to no voltage. The vast amount of PLC processing will be digital logic. The different groupings of ones and zeros below represent blocks of assigned memory. Each one can represent a total value, or a sequence of values, or some data from another device. Each grouping is double the size of the one above it. The smallest amount of memory that can be assigned and used is a single bit, which comes from contraction of binary digit. The bool, the new name for a binary digit in honor of George Boole, who was the father of logical systems with Boolean algebra, contains only a single unit. As a logic memory unit, it represents false or true. As a measurement of voltage, it represents off or on. As a number, it represents either 0 or 1. As a unit, however, it can never be negative. A pair of bits can represent any number from 0 to 3 and can represent 4 different possible states, but it is not a data type. The nibble, although not used in the PLC as a contiguous string of bits, they are extremely important to the electrical industry and programming, as it can represent 16 different states or numbers 0 to 15 and is used for programming using hexadecimal reduction and logical masking. Nibbles, however, cannot be negative. Cents are a contiguous group of 8 bits, a short integer. As a number, it represents any value from negative 128 to positive 127. Its old name was a byte, as in 2 nibbles in a byte. We still use this digital unit dinosaur when discussing memory size: kilobytes, megabytes, gigabytes, terabytes, etc. Now here's a digital puzzle of 8 bits. 2 to the power of 8 equals 256. Now, stranger still, computers, to create colors on your screen, do so by setting the RGB value, the red, green, blue value for each pixel, which are 8 bits. But the bits are set to a maximum of 255. White, for example, is 255, 255, 255, all on to max, and black is 000, 000, 000, all off. But we just saw that a cent was negative 128 to positive 127. We'll get to the discrepancy a little bit later, so hold your thought. 16 contiguous bits creates an int variable, or integer. Formerly known as word, it was the workhorse data type of older PLCs, and you will find most seasoned PLC programmers still refer to it as such. As a decimal number, ints can represent any value between negative 32,768 to positive 32,767. A couple of interesting factoids. Factoid 1, in older PLCs, 16 bits represented the maximum number of points that would be found on an input or output card within a chassis. Factoid 2, When you hear them talk of the 16-bit or 32-bit or 64-bit operating systems, it's telling you the largest contiguous group of bits the processor uses. 32 contiguous bits creates a DINT variable, formerly known as a double word. This is one of the most common data types used and has replaced the 16-bit word for most applications. As a decimal number, DINTs can represent any value between negative 21,474,883,648 to 21,474,883,647. And speaking of 32 bits, 32 contiguous bits also is the size of the Internet Protocol addresses, or IP addresses for short. However, in an odd twist, the 32 bits are broken down into 4 8-bit octets, which are converted to decimal and separated by periods. So 1100, 0000, 1010, 1000, 0000, 0001, 0000 would be translated into 192.168.1.0. And yes, 8 bits are often broken up into 4-bit chunks for clarity. When you have 64 contiguous bits, it creates a lint variable, a long integer. As a decimal number, lints can represent a value of negative 9,023,854,775,808 to, over 9 quintillion. Up to this point, you may not have noticed, but you were being tricked. Well, sort of. Maybe a better way to state this is that you are being heavily discounted on the output of the decimal values of the variables we've been talking about. With binary, each grouping should represent 2 to the power of x, where x is the number of bits. So 2 to the power of 8 would be 8 bits. But all 8 bits on represents negative 127. Whoa, wait a minute, that's not right. Wait a minute. 2 times 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 2 equals 256. What? Wait a minute, wait. The largest number that we had that was close was 255. Oh! This doesn't make sense. A long time ago, PLC programmers ran into a problem. How do you represent a negative number? There's no such a thing as an on-off negative on switch. To do that, you would have to reverse the polarity of the entire card or double up all the devices so that a signal could be negative just to represent a negative number. They had a simpler idea. They decided, with ints and larger, when the leftmost significant bit is turned on, it would make the value higher by 1, but they would multiply that number by negative 1, and instantly making the number negative. Each additional increment would make the number smaller, as in less negative. This actually makes sense if you keep counting, as in adding 1. By flipping 32,767 to negative 32,768 and continuing to add 1, you end up with all ones, which is negative 1. And then adding 1 more gives you 0. The most significant bit is known as the negating bit, or simply the sign bit. However, there are times you require the true value. In those cases, you look at that data type and see if there is one that has a leading U, such as uint, udint, ulint, etc. With the unsigned data types, you are working with the entire true value of the number of contiguous bools in the data type. All of these simple data types consist of a number of contiguous bools. That's it. But each time you create a variable, you must select the data type to determine the variable's numeric range and the amount of memory that the PLC will use. In the next video, we will look at some not so simple variables called constructs. Thanks for watching and see you soon.